In this lecture, I'm going to start the jet transform, right? So how to find the jet transform for the different signals. Before that, we have to compare the Laplace transform as well as jet transform, right? The Laplace transform is for continuous time signals, whereas the jet transform is for discrete time signals. Now, the Laplace transform is an extension of the continuous time Fourier transform, whereas jet transform it is extension of the discrete time Fourier transform. Now, what do you mean by this extension is, see in this continuous time Fourier transform or discrete time Fourier transform, we have some convergence problem. That is, this x of t should be absolutely integrable. That is, e minus dt should be less than infinity. Similarly, it should be absolutely summable. That is, minus infinity to infinity mod x of n should be less than infinity, and it will have the finite number of maximum and minimum value discontinuities. So we have some convergence problem. So whereas the Laplace transform is applicable to the unbounded signals also, that also we discussed, right? So suppose some e power at u of t. So this is something like this. So it will not have the Fourier transform, but it will have the Laplace transform, because this e power at is multiplied with some e4 sigma t, right? So whenever unbounded signal is multiplied with the bounded, so we'll get bounded signal. Yes or no? But we'll have some convergence values, that is region of convergence. So real of a should be greater than minus a or less than a, etc. Right? So that is the continuous time Fourier transform and the extension, right? So similarly, in the discrete time Fourier transform also we'll have some convergence problem, but that can be eliminated when we go to the jet transform. So this is the extension of dtft. Now, so the third point is it can be applied to unbounded signals also, that I explained here, with some values of s. That is, generally we say it is ROC. So the Laplace transform will be converges for some values of the real of s that we have seen. Similarly, this is also applicable to unbounded signals, but with some values of z, that is complex variable. So again, it is defined by the region of convergence. Anyway, that we will see. Now, what is s here? S is a complex number, but it is represented by the rectangular form, that is sigma plus j omega. So this is a real value, this is an imaginary value. Remember, some years back we got some question on this sigma value. So find the sigma value and units of the sigma. That is, this real value is generally we say Napier per second, and the omega is a angular frequency which is radian per second. So remember this one, Napier per second and radian per second. When it comes to jet transforms, jet is also complex variable, but it is now in the polar form, that is magnitude and the phase, that is omega. So what is omega here? Again, angular frequency, so which is radian per second. So r is the magnitude. So magnitude will have no units, right? So r is equal to root of a square plus b square, etc. So this is the magnitude, right? So omega is radian per second, r is a magnitude which will have no units, right? This is about these complex numbers. So this r is magnitude means we'll get these circulars in the jet transform, whereas in the Laplace transform we get strips. See, ROCs in the Laplace transform generally we take wherever pole is there greater than that pole, we'll have the ROC. So the ROCs in the S plane will be parallel strips to this imaginary axis. Whereas in jet transform, or so we can say this jet plane, this is S plane. So in jet plane, we'll have the circles, right? So whatever the pole value, so that will have the radius of A, and the ROC will be greater than this circle. So greater than this means A to infinity is the ROC. So this will greater than this A, the jet transform will be converges. So that is the some differences between this Laplace transform as well as this jet transform, right? Now we will see how to find the jet transform of a given discrete time signal. So that is, so this comes from the when we discuss about the discrete Fourier series, when we apply some exponential input signal. Now what is the output the y of n is equal to some eigenfunction, that is eigenvalue h of z into z power n. Yes or no? This is a complex exponential and this is a system response or transfer function. Now what is h of z? H of z is equal to sigma n is equal to minus infinity to infinity h of n z power minus n. Right? Now if z is equal to simply e power j omega, we will get discrete time Fourier transform. Whereas if z is equal to some complex number, that is r into e power j omega, here r is equal to 1, but here r is some arbitrary value, r into e power j omega. So this h of z is called the z transform. Right? So we are converting the time domain signals into some other variable, that is complex variable, which is called z. So that's why it is called z transform. Right? So if we compare these two, that is, what is the r value? If r value is 1, then dtft, discrete time Fourier transform, dtft is equal to z transform. This is very, very important point. So the magnitude of the radius of the circle is 1, then the z transform on dtft, discrete time Fourier transform, will be equal. Whereas in Laplace transform, when s is equal to j omega, the Laplace transform as well as the continuous time Fourier transform will be equal. So that is about this one. So this is generally called the z transform. For generalized some x of n, that is generalized signals, general signals, what is the z transform? X of z is equal to sigma n is equal to minus infinity to infinity x of n z power minus n. So this is x of z. Now what is the notations we will use is, so suppose x of n is there, so the z transform will be x of z, right? Or this x of z also can be written as z transform of x of n. Right? Any notation we can use. Generally we go for this one, right? So this is the z transform, the formula generally we say. So if I know the x of n, so we can find this z transform. Now we'll see the relation between the discrete time Fourier transform and z transform. So we know that the z transform of any signal x of n is sigma n is equal to minus infinity to infinity x of n z power minus n. Now if I take this complex variable as r into e power j omega, so this will become like this: sigma n is equal to minus infinity to infinity x of n r into e power j omega power minus n. Right? So again this will become n is equal to minus infinity to infinity x of n. If I separate this one, so this will become r power minus n separate into e power minus j omega n. This is x of z. This is the z transform. Suppose this is equation. We know that. So what is the discrete time Fourier transform? X of e power j omega is equal to sigma n is equal to minus infinity to infinity x of n e power minus j omega n. Now this is the discrete time Fourier transform. Now if we compare these two, what is this Laplace, this z transform is the dtft of, see, x of z can be written out like this: x of z is equal to the Fourier transform of, see, in place of x of n, what we are having? X of n into r power minus n. So this is the relationship between the discrete time Fourier transform and z transform. See, so this is x, this discrete time Fourier transform, this is the z transform. Wherever x of n is there, in z transform it is having x of n into r power minus 1. If we compare these two, so the z transform is nothing but Fourier transform of x of n into r power minus n. Now that is the reason this x of n can be any value, right? So is a bounded signal or unbounded signal or stable or unstable. So we are multiplying with some r power minus n. Now that will become the, depending on this r value, it may be raising function, it may be decaying functions. So depending on this r value, so we'll have the finite Z transform, or we can say that finite r is nothing but the ROC of the Z transform, right? So this is about the relation between DTFT. Now from this, so what happens if r is equal to 1? So 1 power anything is 1 only. So that means the Z transform is equal to the Fourier transform of XY, right? See here. So DTFT will be equal to the Z transform when r is equal to 1. So this is very important point, right? So this is about the relation between DTFT and Z transform, how the Z transform is converted into the Fourier transform, right? Now we'll see what is the region of convergence, right? So we know that this Z transform x of Z is equal to Fourier transform of x of n into r power minus n. This Z also replaced by r into e power j omega. Now to converge this Z transform, so what should be happen? This Fourier transform, that is if Fourier transform of x of n into r power minus n converges, then only then x of Z converges. That is the meaning, right? Now if x of Z, the Fourier transform of x of n into r power minus n, so when it will be converges? If this is absolutely summable. So that is indicating the region of convergence. So region of convergence is nothing but so the x of Z converges for some values of some finite values of the Z. So Z is nothing but what? The r, right? So it will have r into e power j omega. So if I take magnitude, so magnitude is nothing but simply r. So for what values of r the Fourier transform converges? So if Fourier transform converges, the x of Z also converges, right? So that is a ROC. Now just now we have seen if r is equal to 1, that means the x of e power j omega r is equal to 1 is nothing but the Fourier transform of x of n, right? That is the Fourier transform of x of n. Now if I convert into the circles here, so this is the real part, this is the Z plane, and this is the imaginary part. I told you we'll have the circles in the Z plane. Now what is the circle? So circle is, the center is the origin always, and so what is the radius of this circle is always the r, and this is the phase omega, right? Now when r is equal to 1, that means the unit circle, this is will be called as unit circle when r is equal to 1. So when r is equal to 1, so at this point, so it will become the discrete time Fourier transforms. At this point, what is this value? Z is equal to e power j omega. So at this point or any point in this unit circle, the Z transform will exist, or we can say the Fourier transform is nothing but Z transform. That is discrete time Fourier transform. So this is about the region of convergence. So we need to find some values of r, or generally we say mod Z, so where the x of Z converges, right? So this is about this. Now we will find the Z transform of the some basic signals. So first I will take the impulse function or impulse signal or impulse sequence, right? So if I draw this one, so this is n. At 0 we will have the amplitude as 1. Now if I try to find the x of Z, the impulse for impulse signal, the Z transform is nothing but n is equal to minus infinity to infinity. X of n is nothing but delta n into Z power minus n, right? So I will use the sometimes this Z or this Z, so no problem, anyone is right. Now so what is this impulse function property? So I'll recall here like this: sigma n is equal to minus infinity to infinity delta n minus n naught into x of n. So what is this? X of n naught. So what is n naught here? 0. So z power 0 is nothing but 1. So the z transform of impulse function or impulse sequence is nothing but 1. Now what is ROC? So for what values of this z or mod z this will converges? So we can say the entire z plane, because there is nothing is there in this. So to say that some for some values of z or mod z or r, this is not valid. So it is always valid for all possible of the z values, right? So that's why it is the entire z plane, right? That is about this one. Second one, we'll see more generalized signals a power n into u of n. This is the x of n, right? Now if you observe, when we written for this discrete time Fourier transform, there we have written this a is less than 1 or 0 less than a less than 1, but in this case we don't write any values of a, because it will converges for the different values of the mod z values, the complex values, right? Now x of z is equal to, what is the formula? N is equal to minus infinity to infinity x of n. X of n is what? A power n u of n and z power minus n. Now what is u of n? U of n will start from 0. So from 0, 1, so etc. What is the amplitude? 1. This is the u of n. So the limits for this summation will become n is equal to 0 to infinity. So we will get into multiplied with a power n. So it will be decaying function actually. So it will become a power n into z power minus n. So again it will become n is equal to 0 to infinity a into z inverse power n. Now when I talked about this discrete time Fourier transform, I have given 3 formulas for this summation. The first formula we have to recall is sigma n is equal to 0 to infinity a power n. So what is the value? 1 by 1 minus a, where a should be less than 1, right? So if I apply this formula here, see, it's looking like a power n. So what is this? 1 by 1 minus a. A is a into z inverse. Now, but what values of this value it will be converges? That is the our ROC. What is ROC? A into z inverse is less than 1. Now this a by z, so z inverse means it will become a by z. So mod a by mod z, so it will become mod z here. So again it will lead to mod z is greater than mod a. So this is the ROC where the z transform converges. So this is 1 by 1 minus a beta. If I write clearly here, so always remember for a for n u of n. So what is the z transform? 1 by 1 minus a into z inverse. What is the ROC? Mod z is greater than a, or we can have mod a also, no problem, right? A. Now this can be written in other way also. This is z inverse, right? Now it will become a by z. So if I take LCM, so this will also become z by z minus a, where mod z is greater than here, right? So you can remember whatever no, if you remember this one, this is very okay. If you can remember this one, this is also okay. So according to your convenience, you remember. So a power n u of n means either z by z minus a or 1 by 1 minus a into z inverse, but the ROC will be same. Mod z is given here. So this is about one basic signal. Now one more is, we take now this is generally we say right sided sequence, yes or no? So if I draw a power n u of n here, so when n equal to 0 it will be a, I mean a power 0 means 1, then n is equal to 1. If a is greater than 1, so it will be the what you call exponentially increasing function. If a is less than 1, it will be decreasing function, something like this. If a is greater than 1, it will be something like this, right? This is. Now we'll see for both cases. Anyway, we'll see one more experiment. Minus of a power n u of minus n minus 1. This is one more signal. This is the left sided signal, right? This is n. So these are x of n. If I assume this is x of n, so n is equal to 0 means, see, it will start from -1, -1, -2 and so on, right? Now depending on a again, so it will be either this increasing or decreasing function. So first we will always assume as a is less than 1. If a is less than 1, so 1 by 2 power minus 1. So in this case it should be a should be less than 1, right? Because 1 power minus 1, right? 1, 2 power minus 1, so 1 by 2, 2 power minus 3, 1 by 2 cube, etc. So it will be decreasing function. When a is less than 1, so it will be increasing function. So remember that one, right? Now how to find x of z? X of z is equal to, so limits will become n is equal to minus infinity to minus 1, and it is minus a power n into z power minus n. This is a formula. The limits is minus infinity to minus 1. So if I take minus outside, so this will become n is equal to minus infinity to minus 1 a into z inverse power n. Now we don't have any formula to get the values of this one. So that's why what we'll do here is we will take one more variable, that is some n is equal to minus k. When n is equal to minus k, so what are the values? It will be n is equal to 1 to infinity. Yes or no? The limits will become 1 to infinity. So I will write here the x of z now will become sigma, minus will be outside, k is equal to 1 to infinity, and this is a into z inverse power minus k. Now you may ask, so infinity to 1, so the limits will be infinity to 1. So infinity to 1 is not possible, so we can directly interchange 1 to infinity also. So that's why I have given like this, 1 to infinity. But if we interchange in the integration, if it is minus infinity minus 1, if we integrate from minus 1 to minus infinity, the minus will come. But that is not the case in the summation. So summation can be interchanged easily, 1 to infinity, infinity to 1, etc, etc. Now again we are not having any formula by this, so again we will assume k minus 1 is equal to some n. Variable can be anywhere, any variable we can assume. Now if I substitute k is equal to 1, so n will become 0. If I substitute k equal to infinity, n is equal to infinity, because infinity minus 1 is infinity only. Now see, the x of z is now minus of n is equal to 0 to infinity. So if I send this minus inside, a inverse z power k. K means, so k is equal to now n plus 1. So from this k will become n plus 1. So it will become n plus 1. Now a inverse into z power 1 is a constant, so it will be outside. So minus of a inverse z will be out. Sigma n is equal to 0 to infinity a inverse z power n. Now it's looking like our formula, that is 0 to infinity a power n. So what is the value we'll get? A inverse z into 1 by 1 minus a. So 1 minus 1 by a inverse z. And what is the condition? The ROC will be a inverse z should be less than 1. So a inverse means z by a. So the ROC will become mod z is less than a, and the value of x of z will become minus a inverse z by 1 minus a inverse z. And what is the ROC? See here, a inverse z is there, so z by a. So if a is going that side, the ROC will become mod z is less than a, right? Now this is not looking like some normal form. So what we do is we'll take this LCM as a. So minus of z by a by 1 minus z by a. Now if I take LCM and cancel, so it will become minus z by a minus z. Again if I take minus out, so it will be z by z minus a. This is x of z. Now what is ROC? ROC is mod z is less than a. So if I recollect, minus a power n u of minus n minus 1. So what is the z transform? It is nothing but z by z minus a only, but the ROC will change, that is mod z is less than a. Now see, whenever we are having minus, we are getting plus. Suppose this minus is not there, we'll get minus here. Just remember. Now if I compare with this one, a power n u of n, so what is the z transform? We got z by z minus a only, but the ROC was mod z is greater than a, right? So what is the difference we are getting? Only the ROC we are getting the different values of z. This will be converges, this will be converges, right? Now how to represent in a circle? So I'm representing for this one first, this one. So this is the z plane, this is the real part, this is the imaginary part, right? Now mod z is equal to a is nothing but a one pole, yes or no? So this is here one pole where the circle is there, a here, and one more 0 is there, that z is equal to 0, so that is 0 here. So mod z is greater than a, that means the ROC is greater than this. So the greater than this means up to infinity, right? This is the ROC of this a power n u of n. Now for this one, what is the ROC? Again we'll have 1 0, one pole at a, right? See here z is equal to a, so positive pole, right? So that's why this side, if it negative means it will become like this. This is the real part, this is imaginary. Now what is the ROC of this one? Mod z is less than a, that means the inner of this circle, so we'll get like this. So it may include the 0 also. This is the ROC, this is the z, right? So we'll have the ROC is in the circles, right? Compared to the Laplace transform where we got parallel strips, right? This is about this ROCs. Next we will find the z transform of this signal. So this signal is nothing but the two-sided signal, right? Now so how can it can be split it? So this you can be split when n is less than 0, this will become b power minus n u of minus n minus 1, plus when n is greater than 0, this will become b power n u of n. Now what is the z transform this signal? Now we have found that if there is a b power n u of n, so what is the z transform? It is nothing but z by z minus b, where the ROC is mod z is greater than b, right? Similarly we found that b power minus n u of minus n minus 1. What is the z transform? Z transform is nothing but, see, we have found b power n, not b power minus n. So first we'll take b power n, it will become z by z minus b, and this is mod z is less than b. But we are having here b power minus n. So how can it can be written like this? So b power minus n means in place of b, can I write 1 by b u of minus n minus 1, this is n. So what is the z transform? Will become z by z minus 1 by b. So mod z is less than 1 by b, right? So this is about this one. So what is the final x of z? Now see, x of z is having it is not having minus, so in the z transform we'll get minus. So minus of z by z minus 1 by b as one value, plus this the second term is as it is, this is z by z minus b. So in this case mod z is less than 1 by b, in this case mod z is greater than b. Now what is the common ROC where the x of z, total x of z will converges? That is nothing but common ROC. So what is the common ROC? Greater than this, less than this. So b mod z less than 1 by b. Now if b is less than 1, so this will become greater, this is lesser only. If b is greater than 1, this will become 2, this will become 1. So for this should be satisfied means the b should be less than 0, less than b, less than, right? So remember this point. Why? If b is equal to 0.5, so this is 0.5, mod z is less than 1 by 0.5, it will become 2. So then only it will be satisfied. Otherwise when b is greater than 1, so this will become 1 by 2, this will become 2, right? Mod z is greater than 2, mod z is less than half. There is no common ROC, so that is not possible. So in this case, b greater than 1 is not possible, yes, because we will not get any common ROC. So one is like mod z is greater than 2, one is less, mod z is less than 1 by 2. So there is no common ROC. Just remember this point. No common ROC. And how to represent this ROC? See, so we'll have two circles. One is smaller one, one is larger one, and we will have two poles, right? So the larger one is 1 by b, the smaller one is b. This is the real part, this is the imaginary part, this is z plane, right? Now see here, so it will have two poles, that is z is equal to 1 by b, z is equal to b I have represented. So I am not representing the zeros because it is not having any role. Now what is the common ROC? See, mod z is greater than b, that means like this, and mod z is less than 1 by b, that means like this. So what is the common ROC? We will get something like this. So this is the common ROC. So it is a ring in the z plane, yes or no? This is a ring in the z plane. That means if any signal is two-sided sequence, right? If x of n is two-sided sequence, we will get a ring in the z plane. The ROC is a ring in the z plane. Now we have seen three signals. One is right-sided, and one is left-sided, and one is two-sided sequences. Now for right-sided, what we got the ROC? We got ROC mod z is greater than a. For left-sided, we got mod z is less than a. For two-sided, we got a mod z less than 1 by a. I am representing now here. So that means for right-sided sequence, we will get exterior of the circle. Left-sided means we will get inner side of the circle, right? Now when there is a two-sided sequence, we will get a ring in the z plane, right? So see, the exterior of the circle, inner side of the circle, the ring in the z plane. So that is the right-sided, left-sided, and two-sided, right? So this is about these some basic signals Z transform. In the next lecture, we will see some properties of these ROCs, right? So what we discussed in the Laplace transform, the properties of ROC, same properties will exist in the Z plane also, Z transform, right?